Okay. Mm, Okay, today we're going to learn about Turing machines. I'm done teaching Turing machines. Let's start reviewing for midterm one. If you want to learn about Turing machines, like, feel free to leave and go to someone else's discussion. If you want to review for the midterm, you're in the right spot. So I'm going, yeah, what's up? I don't think so. Yeah, that's why I'm like, they may be on the final. I think they're usually like a question on the final about it, but based on the exam drop policy, a lot of you may not even need to take the final. So yeah. So here's how this is gonna go. I'm going to start coming up with problems that I've either sometimes they'll be similar to what I've seen, or like, and then I may end up in a spot where the problem ends up being unsolvable, in which case I'll give up. But let's just see where this goes. So okay, so da, 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 da. So the Boeing 737 has been crashing, and I figured out why. Wait, did I start? Da, da, da. Okay, yeah. Yeah, yeah. So it's actually because they aren't placing fat and skinny people properly, which is throwing off the weight distribution. So, in order to make the plane not crash, you need to have triplets of people that are balanced. So we define balance as people that are, or let's say you have three seats like this in the airplane map. You have a heavy dude, a light dude, and a heavy dude. Or you have a light guy, a heavy guy, and a light guy. Determine if the sequence of people is valid. And we define is valid as the plane won't crash. So the reason I did this is back to lab zero, lab one. We said languages are problems. Problems are sets. Sorry, yeah. Languages are sets. Sets are problems. Strings in the languages are yes instances of the problem. So I can write a I can write a regular expression to solve this problem. So I have a sequence of people. They start walking into the airplane and they need to obey this order. What's a regular expression that'll follow this? It's quite simple. H. Assume that you have triplets of people, like because there's three seats per like row. H L, yeah, or L H L star. Oh yeah, yeah, that's true. That's true. You select one of the triplets and you can repeat them as many times as you want. Okay, so now a more reasonable question. Uh, Write a regular expression that contains both 0, 1 and 1, 1 and 0, 0 as subsequences. So we want to write a regular expression that contains both 1, 1 and 0, 0 as subsequences. So what is a subsequence? A subsequence is a sequence of characters that can be obtained by deleting characters from the string and such that only the characters in the subsequence remain. So I want to guarantee that both of these exist as subsequences in my string. So someone give me an example of a string that contains both of these as subsequences. 0, 1, 0, 1. Yes, right? It has the subsequence 0, 0, and it has the subsequence 1, 1. So how can I write a regular expression that captures this? So let's start, yeah. Yeah, let's brute force it. Uh-huh. Uh-huh. So you want to do something like so you want 0, 0 at the end. Okay. And then what did you want to do after? 0 plus 1 star, something like this. Oh, I see what you're saying. And then 0 plus 1 star again. Mm, right. Yes. Correct. So I think another way, so you have the right idea. We want to kind of think about all combinations. Let's start here. How many different ways? Let's say I want all strings. The minimum string length in this language is 4, right? If I need to contain both of these. So how many different ways? Yeah, what's up? Okay, yeah. So the minimum string length is 4. How many different strings of length 4 can I generate that are in the language? 6. What are they? Yeah, so 1, 1, 0, 0. Let's start here. 1, 1, 0, 0. What else? Okay, 0, 0, 1, 1. Uh-huh. 1, 1, 0, 1, 0. 0, 1, 0, 1. Yes. 1, 0, 0, 1. Okay, what else? Is that all of them? Okay. So if I limit my language to strings of length 4, then these length with it, yeah, whatever. If I limit my language to strings of length 4, these are the strings in the language. Now, I can take any binary string and insert it here, 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 or here, add it to any binary string inserted here, 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 or here, and same idea, so on and so forth. So 0 plus 1 clean star is nothing but sigma star, where sigma equals 0 plus, or the set containing 0 and 1. So we put sigma star, sigma star, sigma star, sigma star, sigma star, plus blah, blah, blah. I can't think of one. Can you? So we keep going, blah, 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 blah. Does anyone like conceptually not understand what's going on? Yeah, yeah, yeah. Okay, okay. Great. Blah, blah, blah. So beautiful, my handwriting is. Okay, so let's see, what else can we ask? La, la, la. So then lab one was about recursive definitions of strings, right? So let's move there. So recursive definitions. So we define L to be the language that contains all W belong to sigma star such that every run of zeros in W, every run of zeros in W has length 2, and every run of ones has length 2. So what does that mean? If a 0 appears in the string, it appears twice. If a 1 appears in the string, every instance of the 1 appears twice. So what that means is 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, right? This would be something that's in the language because every run of zeros has length 2, every run of ones has length 2. Uh, wait, actually, hold on. Does every run of ones have length 2 here? This has, yeah, there's a length 6. Okay, every run of ones is a multiple of length 2, and every run of zeros is a multiple of length 2. Or what we can do is every run of zeros is even length. And every run of ones is even length. So 0, 0 appears an even number of times, even number of times, even number of times, even number of times, even number of times. So the way I like to think about this is we define our language, L on string uh, X, let's say, is equal to. So if someone else gave me a string in the language where every run of zeros is even and every run of ones is even, so I have some arbitrary string that's already in the language that someone else gave me. We'll define this to be 0, 0, 1, 1, 0, 0. So every run of zeros is even, every one of ones is even. What's the smallest thing that I can add onto the string to keep it in the language? Yeah, right. So I can add 0, 0 here. I could add 1, 1 here. I could add 0, 0 here. And I could add 1, 1 here, right? And all of these strings would still be in the language because I've added an even run of zeros or ones. So if X is in L already, I can add 0, 0 to the right side, 0, 0 to the left side, 1, 1 to the right side, and then 1, 1 to the, or 1, 1 to the left side. Yeah. If every one of ones is odd length, then I could just put a 1, right? Oh, no, I can't do that because then I could do 1 twice, right? I would probably make two different languages and try to take the intersection of them and alternate recursively between them. Do you want to try it? We can give it a shot. Oh, does anyone have questions about this first? Base cases. Yeah. Do I need to have the case with zeros on the right and left? Probably not. Yeah, I don't need them. So this isn't wrong, but I can also delete half the cases. So I can either, yeah, but the runs of zeros aren't even. So 1, 0, 1, 0 is not in the language. No, no, so I'm defining a run of ones as a consecutive sequence of ones. I want every run of ones to be even length and every run of zeros to be even length. So I want 1, 1, I want 0, 0. That's what I mean. No, a run is the occurrence. Let's define it like this. A run of characters is the number of the same character that appear in a row. So this is a run of 2 zeros. This is a run of 4 zeros. This is a run of 1, 1. That's how I'm defining it. Uh, okay, what was your question? How would you do it if you wanted the number of zeros to be even and the number of ones to be odd? Okay, so define L2 to be the language W belongs to sigma star such that the number of zeros is even and the number of ones is odd. So if someone gave me a string that has an even number of zeros, I could just add zeros to both sides easily, right? So let's see. So I have X that's in L2. And if the number of zeros is even, as I said, I can add zeros to both sides. Also, I didn't put base cases in here. My base case is just epsilon, no? Yeah. Okay. Now I want the number of ones to be odd. So how could I make the number of ones odd? Well, if what if I define a language where the number of ones is even, and then I take that language and then add exactly 1, 1 onto it? So let's define a language L3. Oh, sorry, that's L2, where the number of ones is even. So same thing, x1, 1, 1, 1, x, if x belongs to L3. And then I take an empty string, right? So L3 has only even ones. Then I take a string from L3 and then I add a singular one to either side of it, right? So I take a string, let's say x belongs to L3 now. and then I put x1 or 1x. But there's an issue here. So in this case, I could take a string that has an even number of. Yeah, I think this would work. Yeah, yeah, yeah. Okay. And I can also have epsilon, right? Yeah, in this language. Cool. Yeah. Epsilon doesn't. Wait, no. I'm starting at L2, right? So if I take epsilon, then I have an odd number of ones here. And then I take epsilon, I have an odd number of ones here. Yeah, right. And then if I take epsilon, I have an odd number of ones here. 1, 0, 1, 0, 1. Well, because you want an even number. You want even like runs of zeros, right? Yeah. Oh, I meant even runs. Sorry. Yeah. We're, okay, let's move on to some automata theory. Let's say I want to prove. So the question is L1 X nor L2 regular if L1 and L2 are regular? So that's the question. Is L1 X nor L2 regular if L1 and L2 are regular? So X nor will define the truth table here. So what do we have? So exclusive OR of this is 0. X nor is 1. Exclusive OR of this is 1, so X nor is 0. Exclusive OR is 1, so X nor is 0. And then exclusive OR of these two is 0, so X nor is 1. That's what X nor means. Yay, yucky. Okay. So that's what X nor means. If a string is in language 1 and language 2, then if the string is not in language 1 and it's not in language 2, then it's in language 3. If the string is in language 1, is not in language 1 and in language 2, then it's not in language 3, etc., etc. Well, that's, yeah, it's either in both or in neither. Yeah. Well, hold on. Yes, yeah, it's either in both or in neither. Yes. So is this Yeah, what's up? The intersection, okay, of what? If I get the intersection of L1 and L2, yeah. So let's start there and then see if we can optimize. So very simply, what do we know that regular languages are closed under? So regular languages, whatever, are closed under. What are like some of the operations we know that they're closed under? Union. So union, yep. Concatenation, clean star, intersection, right? Complement, right? So let's use this as a basis. So there's a very, very trivial solution to this. Now that we know this, so we'll define L1 x nor L2 to be L3. Given that we know these operations are regular, and given that we know that that's the definition of x nor, what can we do? Yeah, the complement of the union with, yeah, yeah. So what we can do exactly as he said. So we can define the things that are in the language as complement of L1. So it's not in this and it's not in that, right? So complement of it's not in L1 and it's not in L2. If both of those things are true, then it's in L3. Or if it's in L1 and it's in L2, yeah. And instead of or, I should put a union operator. So, sorry. The answer intersects, meaning? Okay. So, oh yeah, L1 intersection. Yeah. Sorry, yeah. Boolean algebra. Yes. Yeah. Fine. So it's L1 intersection L2, or okay. So that's it, right? So now we claim that L3 is regular. Why? If L1 is regular, its complement is regular. If L2 is regular, its complement is regular. If you take two regular languages and take the intersection is regular. We know that L1 is regular and L2 is regular, therefore its intersection is regular. If you take the union of these two regular languages, it's also regular. Yeah. If you try to do the exact same question, there's no guarantee. So the thing is, it may work if you pick a specific irregular language, but it won't broadly work for all irregular languages. So let's do this. So going off that line of reasoning. Wait, does this make sense to everybody? Yeah? Okay. So um so we know that the let's do some true false. So the intersection of two irregular languages is always irregular. True or false? So who thinks true? Here. Who thinks false? Wait, raise your hand for true. Raise your hand for false. Raise your hand if you didn't raise your hand. Okay. So, um, someone who thinks false, why do you think it's false? Someone who thinks true, why do you think it's true? Yeah, great. So this is a known irregular language, right? And then we take b to the n, a to the n, which is also irregular. We take the intersection of these two, and then we get the empty set. Well, yeah, well, I'm sure. This okay, so and then this language is regular, right? No, you get the empty set. So if I say that this language is the set of a to the n, b to the n, such that n is greater than or equal to zero, and then b to the n, a to the n, such that n is greater than or equal to zero. I'm sloppy with notation here, but they're two sets, right? So the intersection of two sets will always be another set. The empty set. Well, you can now go into this theoretical debate if the set contain. So these aren't the same. So the set containing the empty string. So the question is the set containing the empty string equal to the empty set? Both of them are regular, right? So who cares? Well, then, well, if that's on the exam, then I'd fail. So the debate was is is sorry. So I feel like the answer to this is no. But I also feel like from a set theoretic perspective, like if you just look at sets, oh, you know what? It depends on how you define your alphabet specifically, right? So, but the thing is, implicit in the alphabet definition, when you say 0 and 1, epsilon is like implicitly there. So, yeah. Well, it's an empty set, right? Okay, whatever. Who cares? Okay. The answer is false, right? Okay, great. So, let's move on. So, we know that if I take a regular language and intersect it with an irregular language, and I get some L output, is L output regular or irregular? What do you think? I take a regular language and I intersect it with an irregular language. Is the output regular or irregular? Yeah. We can't say. Yeah. It's like this quantum thing. No. So, can't say. Can you give me an example for each? Hmm. Right. So we take some empty set, we intersect it. Sure. Okay. So then this is now regular, right? Regular. So now this was a regular language, and then this was an irregular language. But then, and then the output was regular. So say that one more time. So sigma star, yeah. So we'll take the same one. And then this will just be the irregular language, a to the n, b to the n, such that n is greater than or equal to 1. So now we have a regular language intersected with an irregular language. And then the output of this is an irregular language. So if you take the intersection of an regular and irregular language, then the output can either be regular or irregular. Okay, now let's say this. Let's say I take a regular language and then I intersect it with some unknown language, and then the output of that is irregular. Is L question mark regular or irregular? Right. So the claim is that L question mark is irregular. Why? If L question mark was regular, then this output would have to be regular. But since this is the only way you can get an irregular language here is if this L question mark was irregular. Okay. So what are we doing on time? 9:41. That's not helpful. Okay, let's see. So for every L star L star is regular. True, false. Yeah, for every L. So no, that's yeah, just testing reading comprehension. So if L was context free, then you took clean star. There's no guarantee that it's regular, right? Okay. So false. Da, da, da. Okay. I have an NFA, which is M, which is equal to delta. What else is in here? Q sigma. I don't remember the order. And then I make a new NFA, NFA M prime, which is equal to the same start state, the set of accepting states minus, sorry, the set of all states, Q, from the original NFA, minus the accepting states of the original NFA. I keep the same transition function. I keep the same set of states, and then I keep the same alphabet. Is the language accepted by M equal to the language accepted by M prime complement? Does everyone understand the question? So I have an NFA M, which is a 5-tuple, and I formally define it as these 5 thingies. And then I make a new NFA M prime, except the set of accepting states now is equal to the set of states in the old NFA minus all of the states that were in the accepting states of the old NFA. And then I have the same transition function, the same set of states, and the same. So intuitively, if what does this look like in a diagram? If I gave you a diagram of M, like I drew it out, right? What would M prime look like in a diagram? You flip all of the accepting and rejecting states. So diagrammatically, does that make sense? Okay, so is the language accepted by M equal to the complement of the language accepted by M? Yes. Are you sure? Yeah. I'm asking, is this true? Yeah. Yeah. So why is it not true for NFAs? Right. So let's give you a single counterexample is enough to prove that this is wrong, right? So let's say I take this NFAS, uh, and I make this to be the accepting state, and then I have an epsilon transition, and then I go, let's say, here, right? This is M. M prime is the same NFA, but I've switched the accepting and rejecting states. So what's the language accepted by the first NFA? Sigma star, right? So 0 plus 1 clean star. What's the language accepted by the second NFA? Sigma star. And they're not complements of each other. So the reason flipping the accepting and rejecting states doesn't work in an NFA, but it works in a DFA is because of the epsilon transition. The non-determinism doesn't guarantee this. Does the question make sense to everybody? Yeah? Okay. Uh, what about, I know epsilon transitions are one reason why it doesn't work. What if you have duplicately defined transitions? So in that, an NFA, when you take a single character, can lead to a set of accepting states, right? So that's also non-determinism in and of itself. Because you don't know which path it's going to take. So let's try it out. So he says, if we get rid of the epsilon transitions, will this work? Yeah. Yeah, if I just change that epsilon to be 0, 1, it'll still work, right? So in the same diagram, the question is, if we get rid of epsilon, does this work? And then, as that student pointed out, if I just change this epsilon to be, right? So it doesn't work. Hold on. No, it still doesn't work because they're not complements, but the languages accepted are not the same. Because this needs at least 101, right? So this is actually 0 plus 1 plus now. So I need to take at least 101. So this language becomes, in order to reach the accepting state here, I need at least one of these. And then, yeah. But either way, they're not complements. So let's do some, what time is it? Language transformation. So we'll define delete 2 of x to be, you know what? Maybe I should just take a question from a past exam, because if I don't define this language properly, the language transformation problem can be very hard. So why don't I do that? Let's take this one. Also, it's possible that the language that I come up with could actually not be like a transformation that's regular too. So this is from, oh, it says here, midterm 1, spring 2022. So let sigma be 0, 1. Let L be the arbitrary language over sigma. So L is some regular language. We don't know what L is. Define the operation 2 is wild L as follows. 2 is wild L is equal to ABX, such that A is a character in the alphabet set, B is a character in the alphabet set, and ACX is a string that is in the language. So what does this tell you immediately? So the strings accepted by L are at least of length 3, assuming that you don't put epsilon for one of them. If you strictly say this belongs to the language and A and B belong to the character set, actually, yeah. So C also is a character in the character set, right? So all the strings are of at least length 3. To summarize, oh, okay, I'm wrong. To summarize, every string of length 2 or longer is an L, and is also in 2 is wild. Additionally, you can take any string W from L, change the second character to anything that you want, and the resulting string will be in 2 is wild L. Show that 2 is wild L is regular by constructing an NFA. You may assume that the DFA for L exists as follows. So what this means is, I have a regular language L, and I have a bunch of strings in the regular language L. If I apply a transformation to that language, where I generate the set of all strings from L, where the second character is replaced with any other character from the alphabet, the resulting language is also regular. Does that make sense to everybody? So let's build our NFA M prime. And then conceptually, just to be clear, I like diagrams. So do, 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 do. Input string, W. I have this desk here. The desk has a light that may glow up. I take this character. I take the first character of the string, and then I pass that directly in. So this is the first char. I take the second char of the string, but they said 2 is wild. So this is wild. So I need to decide, do I pass this character in directly, or do I pass any other character from the character set, right? So if my character set was, hypothetically, did they say sigma is 0, 1 here? Yeah. So if my character set is 0, 1, and 2 is wild, and I probably shouldn't put zeros here. Let's put X's for characters. Then I switch this. I try to put a 0 in, and then I try to put a 1 into the machine. And then after doing that, I simulate the rest of the string on the DFA normally. So simulate rest of string normally. This is my M prime that I'm building, and this is M. Is the strategy clear? Does anyone raise your hand if you want me to go over it again? Or don't understand? Yeah. Okay. So I'm given a regular language L. I don't know what the language is. It's some arbitrary regular language over sigma. The claim is, if L is a regular language, and I enumerate all of the strings in L, and I flip the second character of every string in L. If I flip the second character of every string in L, if it was a 0, make it 1. If it was a 1, make it 0. Or I pass the character in as is without flipping it. If it was a 0, it's still a 0. If it's a 1, it's still a 0. And I enumerate all of those strings. So if L was the language, hypothetically, if L was, let's just say this, right? I want to say that if this L is my finite language, I can prove that the language obtained from transforming this. So if I apply the operation 2 is wild, I'm going to get 4 strings as outputs. I'm going to get 0, 0, 1, 1. I'm going to get 0, 1, 1, 1. 0, 0, flipping this, 0, 0. And then 0, 1, 0, 0. So they call it 2 is wild because the second character is like a wildcard character. It can be anything. So if this language is regular, when I apply the 2 is wild transformation, then this resulting language is also regular. Does that make sense? So I have a black box oracle that accepts this language over here, that accepts this regular language. I'm trying to prove that this language is regular. So I enumerate all of the strings in this language, in language L, flipping zeros and ones or passing them in as is. And if this DFA oracle accepts the resulting string, then the language is regular. Then the string is in the language. If it does the set of states, I'm going to have is, so I'm building M prime, which is equal to S prime, A prime, delta prime, sigma prime, and then Q prime. So let's think about the set of states that I need. So what do I need to do? I need to keep track of whether or not I've seen the second character, right? So in the scenario that I've seen, there's 3 cases. I'm in the first character. The first character I pass into the machine directly. On the second character, I try passing it into the machine and I try flipping the bit. On the third character, I just pass it in as is, and I pass the rest of the string in as is. So let's define 3 flags. Technically you need 2, you could switch back, but let's define 3 flags in order to do this. So I take my original set of states Q from the DFA. This is my DFA, and it has S, A, delta, sigma, ligma, Q. I take Q prime and I define it as the original set of states with 3 flag variables. We'll call it first, second, and then last, to keep track of that. We will, to say that my character set is going to be the same. Remember, the character set is just input characters. So my input characters are still going to be the same, or still going to be the same. So what's my accepting state going to be? The new NFA that I build to accept 2 is wild will accept the string only if the DFA for L accepts the string. So 2 is wild will only accept the string if the DFA accepts the string. But it's not just the DFA has to accept the string. It needs to accept the string after reading this character. No, so it's not that you get rid of the accepting state for one character. Yeah, you can get rid of the accepting state, right? So it can, it depends. Okay, let's be very clear. First is the state that you are in before passing the first character in. Second is the state that you're in before passing the second character in. So what you want is to accept at third, because the third state is after you have passed the second character in to the end. Well, so here's the thing, right? This DFA is guaranteed to accept strings. It only accepts strings of length 2 or bigger, right? That's what it says in the problem. So the language consists of strings of length 2 or bigger. So we don't even really need to explicitly worry about that. Yeah, L, it says, right? It says guaranteed of length 2 or bigger. Does it not? Yeah. So we take the set of accepting states of if my old DFA was in an accepting state and I'm done passing in the second character, my new NFA should accept the string. Okay, what should my transition function do? Okay, sorry, what's my new start state? I said that first is the state that I'm in before passing in the first character, right? So I'm going to start here in the same state. So what is the tuple that represents the start state for the NFA that I'm in? Yeah. Yeah. Or S, yeah, sure. First, right? Okay, now the transition function, delta prime. So here's where things get tricky. If I'm if I am before feeding the first character into the machine, if I'm about to feed the first character in, I just feed it in directly. I don't try flipping anything. So we'll do that. So delta, if I'm in state delta prime of if I'm in state s comma first, and then I read in a character c, it doesn't matter if it's a 0 or 1. What state do I end up in? I end up in the state that the DFA would be in after reading character C. So I end up in the state that the DFA would be in, starting from my start character, reading C. So how do I find that? I take the transition function for the original DFA from the start state, and I read character C. Okay. Now, where is my new NFA? My new NFA is now in its second position, right? I moved from first to second. And I'm using set notation because I'm building an NFA, even though I'm transitioning only to one state. Does this make sense so far? Okay, great. Now, I'm in some arbitrary state, Q, comma second. Okay? My NFA is in a state Q, comma second, and I read in a new character from my input string, C. So I'm here now. In this diagram, I'm in this second state. What do I need to do? I need to try passing in the character as it is, or I need to try changing the character to any other character in the alphabet. So if I read in character C in the second state, no, sorry, that's way too many fucking things. Okay. Well, what does that mean? I said I need to try 0 and 1. So I take the state that my DFA is in, Q. I try putting a 0 into it, see where it ends up. And now I'm in the third state of my NFA. Or I take my DFA and then I try passing in a 1 and then transition to the third state of my NFA. Now what do I do? So I've tried all possibility of second characters. Now I'm in the third state or after, I just pass the string into the machine. So I'm here now. in this portion of the diagram, in this third state, from here to here, I just pass the rest of the string in normally into the DFA. So if I am in some arbitrary state, Q, and I read the third, and I'm in the third state of my NFA, and I read in the input character C, I place C and I pass the string in as if I'm reading character C into the DFA. So that's the transition function Q applied to C. And my flag doesn't change. I'm still in the third position where I've already passed in the second character. And that's it. Questions about this? Yeah. I only need two flags. I could have switched back. I did it for simplicity. Right? I could, after this, I could have switched back to first. And questions? Okay. Study hard. Enjoy your weekend. Oh yeah, I'm sure you guys know the videos are online, and there's a link to notes if you want them. So next, yeah, it's a review session. Yeah, let me stop recording.